Okay, this is a unit test. And in the first question, we were asked, by titration, 23.4 mLs of 0.2435 molar sodium hydroxide is needed to neutralize a 0.6958 gram sample of an unknown acid. What is the molar mass of the acid if it is monoprotic? That's the first part of the question. So I began by writing the equation. Sodium hydroxide is titrating an unknown acid. Here's the proton that comes off the acid. The rest of the acid is going to be identified as A. When you get an acid-base reaction, you get water as one of the products, and the conjugate base of the acid plus the counter-ion that goes with it. Here's the concentration of the base used in the titration, the mLs delivered, and how many grams of the acid you had. So the first thing I did was to find out how much base was used. So the molarity times the volume of the solution. Remember to convert to liters if you're given a quantity in milliliters, or else your answer will be 1,000 times too large. We get 5.6979 times 10 to the minus 3 moles of the base and the acid, because it's a 1-to-1 stoichiometry. 1 mole of the base neutralizes 1 mole of that monoprotic acid. If it had been a diprotic acid, then you would have had to include here a stoichiometric coefficient. But because it's 1-to-1, the moles of base equals the moles of acid. Then, because we know the moles of acid and we know the amount, the weight of the acid that was used, we can find out the molar mass of the acid, because the moles of protons that were on the acid is also going to give you the moles of the acid itself, because for every mole of the acid you get 1 mole of protons, as it were. So 0.69 grams divided by the number of moles gives you 122 grams per mole, and then you're only allowed 3 significant figures, so that's the molar mass of the acid. Then we continue the second half of the question. It says, elemental analysis of the acid indicates that it is composed of 5% hydrogen, 68.8% carbon, and 26.2% oxygen. So we assume the 100 gram sample, which gives you all the percentages turned into gram quantities. We then divide by the molar mass of each one of the elements involved. It gives us a ratio. Then we take the lowest number in that ratio to find out, to try to get an integer ratio on our empirical formula. As it turns out, we get 1, 3.5, and 3 as our tentative empirical formula. But you can't have half of an atom. So we multiplied everything by 2, and it gave us 276. That's our true empirical formula. We then take the empirical formula, and we find the empirical formula weight, symbolized by EFW here. 7 times 12, 6 times 1, 2 times 15 for the oxygen. It gives you 122 grams per mole, which confirms that we have the same substance, because we earlier found out that it was 122 grams per mole. So that's a nice confirmation of the first half of our question. So the formula is the same as the empirical formula, so we end up having the same answer. The molecular formula is the same as the empirical formula in this case. Had it not been, suppose instead we had gotten an empirical formula of 122, but this had been 244. By making a ratio of 244 to 122, we would find out that in fact the molecular formula is twice the empirical formula, and we would have multiplied the empirical formula by 2 to get C14H12O4. But that didn't happen in this case, so it turns out the empirical formula is the same as the molecular formula. In question 2, we're asked to titrate a sample of seawater, which contains chloride ions, with silver nitrate. Silver nitrate provides silver cations, which form an insoluble precipitate, silver chloride. A very insoluble precipitate, that's why it's used. It's very good for using as a precipitant for chloride anions. We're given that there was a 25 milliliter sample of the seawater. The density of the seawater was 1.025, and we're told how much the concentration of silver nitrate was and how many milliliters we used to titrate it. So I again used N is equal to mV, molarity times volume is equal to number of moles, and we used 1.276 times 10 to the minus 2 moles of silver nitrate, which means we also had that same number of moles of silver, and that because it's a 1-to-1 ratio, 1-to-1 stoichiometry, for every 1 mole of silver cations present, you will titrate 1 mole of chloride anions. So that will tell us that we also had 1.27 times 10 to the minus 2 moles of chloride anions. I then multiplied by the molar mass of chlorine, which is 35.45. It found out how many grams of chlorine was in our 25 milliliter sample. Because the question asks us to give a percent by mass, we need to convert this volume of 25 milliliters into a mass. So I use the density equation. Density equals mass over volume. I transpose the density symbol, rho. It's the Greek letter rho. It looks like a P with an extra long tail. Rho V is equal to M. And the density times the number of milliliters gives you 25.625 grams of seawater were in the sample. And then we do percent chlorine calculation by dividing the mass of chlorine by the mass of the sample that it was in. Multiplying by 100, we get 1.766% chlorine by mass. We're allowed 4 significant figures in this calculation. The third question asks us to calculate the phosphate concentration in a mixture that contains 3 sources of phosphate: potassium phosphate, aluminum phosphate, and calcium phosphate. The one thing that you need to notice in this problem is that the calcium phosphate yields 2 equivalents of phosphate. The potassium phosphate has 1 mole of phosphate for every 1 mole of potassium phosphate. 1 mole of aluminum phosphate will also give you 1 mole of phosphate. So the one tricky part is to remember that 1 mole of calcium phosphate will give you 2 moles. I put the 2 in the wrong place, I just noticed. 1 mole of calcium phosphate will give you 2 moles of the phosphate anion. And if you forget to do that, your quantities will be wrong. You'll get the wrong answer. Here I'm finding out the molar masses of each one of the 3 substances involved. We're told we had a 14.5 gram sample, of which 84.3% was potassium phosphate, which means we had 12.2 grams of potassium phosphate. I then divided by the molar mass of potassium phosphate to find how many moles of it I had, and it would also tell us how many moles of phosphate. Likewise, 14.5 grams times 10.9% of aluminum phosphate gives me 1.58 grams of aluminum phosphate. Divided by the molar mass gives you 1.29 times 10 to the minus 2 moles of aluminum phosphate and the phosphate anion. And here comes the tricky part. The 14.5 grams of calcium phosphate, 4.8% of that sample weight was this stuff. Divided by the molar mass of the calcium phosphate gives you that many grams. And then we throw in this stoichiometry ratio to account for the fact that for every mole of calcium phosphate, 2 moles of phosphate is released into the solution. So that gives you 4.48 times 10 to the minus 3. Now I add up all of those 3 numbers that I got. So I add up the number I obtained here, this one, and this one together. All these 3 are in the same solution. That's the concentration of it. That's how many moles of phosphate is produced by each one of the substances. And then I divide it by the total volume of the solution to find out the phosphate concentration, which is, after significant figures have been taken into account, 0.6 molar. And lastly, we're asked, a tanker truck carrying 3.2 times 10 to the 3 kilograms of concentrated sulfuric acid solution tips over and spills its load. If the sulfuric acid is 95% sulfuric H2SO4 by mass and had a density of 1.84 grams per milliliter, how many kilograms of sodium carbonate must be added to neutralize the reaction? In this question, they give you a density, but you never actually use the density. So that throws some students off because they want to use all the numbers that are given in the question, but once in a while, they do that in a test, just to test your understanding of the material. You don't always have to use every single number that's given in the test. Very often you do, but once in a while it will happen that you get a piece of information that's not useful to solving the equation. So it was 95% pure. There was 3,200 kilograms of it. So that means there's 3,040 kilograms of H2SO4. We converted it to grams by multiplying 1,000 grams per kilogram, allowing us to cancel kilograms. We then divide by the molar mass of sulfuric acid. Here's the mass of hydrogen, here's the mass of sulfur, here's the mass of oxygen. And we find out that we have 3.09 times 10 to the 4 moles of sulfuric acid. And that we need the same number of moles of sodium carbonate. You notice I did the neutralization reaction. I didn't give you the net reaction because carbonic acid actually breaks down into water and carbon dioxide. But we don't care about that. All we care about is getting the stoichiometry here. 1 mole of sulfuric acid will be neutralized by 1 mole of sodium carbonate. So we need that many moles of sodium carbonate to neutralize that many moles of sulfuric acid. So once I have that number, I'm going to multiply it by the molar mass of sodium carbonate. Here's the sodium, two sodium atoms. Here's the carbon atom. Here's the 3 oxygens. We get 3.2 times 10 to the 6 grams of sodium carbonate needed. We convert back to kilograms by dividing by 1,000. We get 3,285 kilograms necessary. We're only allowed 2 significant figures in the answer because we were only given 2 significant figures here. So we round it to 3.3 times 10 to the 3 kilograms. So 3.3 tons of sodium carbonate is needed to neutralize the acid spill. And again, when you get an answer, check it for believability. You know, if you do a big long calculation and you know that you spilled 3,000 kilograms of something, it's not going to be cleaned up by, say, 3 kilograms. That right away should tell you that you've made some sort of conceptual error or you've forgotten a conversion factor. Always go back and check if you see a strange answer that makes you feel like you might have forgotten something. Each one of the red arrows represents what I was looking for when I corrected the test questions. Are there any questions? Okay, let's end it there.